Hello class, welcome back to Introduction to Material Science and Engineering. In our last lecture we discussed phase diagrams and we discussed different ways that we can change temperature and composition and alter our microstructure, and we gave some hints on why and how we might do that to achieve microstructures that gave us specific properties we needed. Most importantly, we discussed the fact that phase diagrams are an indication of what we would get if we allowed things to happen only at equilibrium. We gave cooling an infinite amount of time, we changed pressures very slowly, we changed composition slowly, and while that's great, that may not always be what we want. Sometimes not letting things happen at equilibrium and not achieving the equilibrium microstructures predicted on our phase diagrams is exactly what we want to do. And so in this chapter we will go over more in detail about what the phase diagram gives us. We're going to step into a little bit more of the balance of thermodynamics and kinetics of what thermodynamics wants us to have versus what kinetics will allow us to have, and then how we can actually play those against one another to tailor microstructures for specific applications. Although this is general for any material, any class, we're going to use a couple of very steady Freddy examples, very classic, so to speak, examples, better phrased, that have been used for decades in materials applications, namely steels and some heat-treatable aluminum and copper beryllium alloys, to showcase the role of microstructural transformations and tailored microstructures for given applications using these concepts. So that said, you can use these same concepts for any kind of phase transformation in anything, including things that are already fabricated composites. You can put these ideas together with fiber reinforcement or use them as alternatives. So we're going to speak very general with those couple of specifics. Okay, so microstructural transformations basically is using phase changes to achieve strength and toughness or other material properties that you can't get with a single phase microstructure. This is basically why we would ever use a mixture of materials that was not a solid solution, because we need something a solid solution can't give us. So given that we are plunging into the world of multi-phase microstructures, we're going to look at how they form. And that is the realm of nucleation and growth, which is where we're going to pit thermodynamics against kinetics. We're going to include the idea of strain energy and undercooling as thermodynamic drives. Just put them up there on the table and see how we can use those to give us microstructures we couldn't have otherwise gotten at equilibrium. We're going to look in the context of steelmaking at stable phase microstructures. What can we get when we follow the phase diagram more or less closely, and what we might use them for, advantages and disadvantages. There's certainly a lot of them out there. And then what happens when we throw equilibrium out the window and go for metastable phases. How stable are they? Are they practical? What can they give us, and where would we use them? And we're going to end this discussion with precipitation hardening, which we actually started back in our phase diagrams discussion, looking way over on the left or right hand side of a eutectic phase diagram or eutectoid phase diagram, and look at what happens when we delay the onset of the formation of that second closer to room temperature solid precipitate precipitating out of solid solution. Okay, so we're going to start a little bit back like we did with phase diagrams and start going from what are phases to why do phase changes occur. So this starts us back into the realm of thermodynamics. Phase changes occur under the influence of a thermodynamic drive. Like every other change in materials, this is done to reduce the overall energy of the system, but this time in response to a state variable change. And remember, the definition of a state variable is any descriptor of the system which is path independent. So entropy, enthalpy, Gibbs free energy, temperature, pressure, chemical potential, and we're going to throw a new one in, elastic strain energy. We touched on that way back in defects when we introduced the idea of the strain energy associated with vacancies and interstitials and dislocations. Anytime that we started moving the majority of our atoms in our crystal off of their equilibrium positions, because elastic strain is effectively path independent and instantaneous, we can look at the cumulative elastic strain as basically a state variable, just like voltage, where we're moving charge off of its equilibrium potential, so to speak. Then we're going to look at what's actually involved in changing a state variable, or what happens in response to it. Atoms or molecules will reach that lower energy state only by moving. They don't get there instantaneously, which also becomes very important. And which way would they want to move? So just 3 hypothetical examples. We know that the atomic packing fraction of an FCC or an HCP crystal is higher than a BCC. So it wouldn't be hard to imagine that if we increase the pressure of a crystal that was a body-centered cubic and it was able to move and have an allotropic phase transformation, it might want to transform into a facer hexagonal close packed. So if you were a geologist looking deeper into the Earth, you might expect to see a greater fraction of closer packed crystals. All other things being equal, of course. Obviously, if you decrease temperature, things will tend to want to solidify from a liquid. If you increase strain energy by cold working something tremendously, a huge reduction in area in a single pass, say at temperatures below recrystallization, you're going to encourage the atoms to want to rearrange to new strain-free grains, which of course is the drive for recrystallization, which we saw in our strengthening chapter. So knowing which way things are going to want to move based on thermodynamic impetus or drive, let's get to work with the kinetics, which is how they actually get there. So we start with nucleation, which is the first step to getting a new phase. And we're going to describe this in the context only of crystalline materials. There are analogs in polymers. It's more applicable with crystalline polymers. But depending on exactly which state variable change you're talking about, obviously there's some cases where amorphous polymers could change their configuration. But for the context of this chapter, just think in terms of crystalline materials, and we will mostly be confining our discussion to metals. So imagine a metal in a liquid or in a solid solution, and we've decreased its energy by cooling it or by allowing it to get to a point where it wants to release some strain energy. The first thing it's going to do is form very, very small regions where that thermodynamic change has occurred. We've gotten rid of the strain in the lattice. We've reorganized to the crystal structure corresponding to the new lower temperature, higher pressure, what have you. So these are the small seeds or crystallites from which we will grow the new stable structure corresponding to the new set of state variables. These are the nuclei. Okay, so these are going to grow, and hopefully, if they're allowed to, in response to the new set of state variables. Now, as they're growing, they're in dynamic equilibrium with the old structure. Just like if you think back to your sugar and water solution, those sugar crystals in the syrup, if they've precipitated, they're not just sitting there not interacting with the water and the sugar in the syrup. Sugar molecules are constantly being added and dissolving in a dynamic manner, and if the rate of dissolution and precipitation is the same, you're at equilibrium. Well, in this case, you're hoping that the rate, if you want the phase change to occur, you want the nuclei to grow, the rate of growth has to be greater than the rate of dissolution. So that dynamic equilibrium has to be shifted from a net zero rate. So we can look at the rate of growth of the nuclei as and it's an energy balance first. So we can think, here's the energy balance to nucleate a new phase and keep it growing. So adding all of these up, on the growth side, we have a volumetric energy reduction, which increases with an increase in the variable that's driving the phase change. So if we're trying to precipitate something from a liquid, we would be looking at undercooling below the precipitation temperature. Or if we're looking at an allotropic phase transformation, like our FCC iron to our BCC iron, we would look at how far below the equilibrium phase transformation temperature we were. If we were looking at recrystallization, we'd be looking at how much strain energy did I put into that metal on my last coal working pass. So this is, on the left-hand side of that balance is our energetic drive based on a single or multiple state variables. And this will be per unit volume of material every time. So greater drive means greater amount of material affected per unit drive. On the flip side, though, every time we form a new phase, we're forming a new surface. And as we discussed back in our defects section, our surfaces, these are 2D surfaces, they have a higher energy just because everything isn't all in its perfect crystalline orientation and equilibrium spacing. So we're decreasing the energy per unit volume by forming the new phase, but we're increasing the overall surface energy of the material by making a new surface. So obviously, if these are completely energetically balanced, nothing's going to grow and nothing's going to shrink either. If the energy to form the new phase on a volumetric basis is greater, the phase grows. If the surface energy is greater, it might shrink. So if we have, say, a small undercooling, a small delta T, or only a little bit of plastic strain, we don't have a lot of drive to form a new phase. So we'll probably have a really slow nucleation rate. And because we're trying to not form any more surface than we need to, because that's energetically expensive, we'll end up with a lot of a very few large crystals, very few nuclei, large crystals at the end, because that maximizes our volume of material changing, which is the drive for the change, while simultaneously reducing the surface area. And flip side, if we give a tremendous drive for our phase change with a lot of undercooling, or big temperature below the phase transformation, or above if we're heating, lots of plastic strain, high strain energy, we're going to be able to overcome the need to create a lot of new surface. So we'll have a fast nucleation rate, lots of nuclei, which will grow together and form many, many small crystals. So if you're thinking in terms of the properties that we would need from a microstructure, just from this, if all we were going to do was nucleate one new phase and then go put the material into service, most of our mechanical properties, we remember, are favored by a refined grain structure, lots of small crystals. So already we can think, if I gave a phase transformation process a tremendous drive to occur, I would probably get a nice grain refined structure. I'd get a nice small grain sized microstructure, which would give me a high strength. I could use the Hall-Petch relationship to calculate maybe the increase in yield strength. So I'm already seeing if I had high strain energy from my last cold work pass or a high degree of undercooling, I might get a really good microstructure for high strength applications, say, mechanical properties. So just one potential application right there with our first new phase change. Now we can do a little bit of math and start looking at an energy balance a little bit more closely. So here's another radius of our new phase. So we're looking at a single nucleus, little nuclei of crystallite growing. We can invoke the concept of activation energy, reference back to our volumetric drive to grow versus our surface energy drive to not grow, and say at what point, at what size of a nucleus would we have to get before the net drive to grow is always going to be in the positive, or the free energy change associated with growth is negative. Because remember, a free energy change that's negative usually corresponds to the direction of spontaneous change. Apologies to those of you who have not taken much chemical thermo or physical chemistry. This is in reference to thermodynamic state variables like Gibbs free energy corresponding to the direction of spontaneous change at constant temperature and pressure. So in this case, our delta G is referring to a Gibbs free energy. So if the Gibbs free energy change is negative, that means something will spontaneously happen. So they're used interchangeably. So if we look at our plots, say we have some spherical nuclei growing, which wouldn't be unusual maybe if we were nucleating something out of a liquid. And of course, a sphere minimizes surface, so that certainly seems like an energetically favorable configuration. Well, the change in energy in the system with the change in particle size will simply correspond to the surface area of that spherical nucleus times the surface energy, which is the energy per unit surface area there. Actually, this would be surface energy, not surface tension. So 4 pi r cubed, or excuse me, 4 pi r squared, very important squared here, times the surface energy. The volumetric free energy, which is forming due to the undercooling or the unit strain energy, is going to be proportional to the volume of the sphere times whatever increment of free energy that we're getting as a result of the phase change. So, of course, that's negative, being in the direction of spontaneous change. So just like our equilibrium force balance way back when we were looking at equilibrium interatomic spacing due to attractive or impulsive forces, we can do an energy balance in terms of the radius of our nucleus and say, well, when our total free energy change for adding a new increment of radius starts going negative, that free energy change, or the change is zero actually, excuse me, pardon me, not a force balance, we're at an energy balance. The change will be spontaneous. So we're looking at the maximum in the curve, corresponding to the vertical dotted line. Excuse the errors in speaking here. So when our delta GT, our total free energy, hits a maximum, and the next increment of radius increase will result in a decrease in total free energy, the nucleus will grow spontaneously. So looking back at the driver, our light blue volume bulk free energy, our delta GV there, we obviously have the volume of the nucleus, but then we have the change in free energy per unit volume. Well, we're growing the nucleus. Okay, so and this is, by the way, the new phase nucleus, not to be confused with, say, the nucleus of an atom, just for reference there. So as we're growing this new little crystallite, we're growing the radius, we're growing the volume. So that's your 4/3 pi r cubed. Can't change that much. In fact, you're trying to change that. If you want to get a bigger free energy released, a bigger delta G sub V, you need to, per unit growth of the nucleus, you have to get a bigger free energy on the right-hand side, the delta G sub V with the Greek letter, and that's the free energy per unit volume. So for every volume that we add to our new growing phase, we want a big energy release, not a small energy release, or surface energy will win. Things that change delta G sub V with the Greek V. So the per unit volume free energy release as related to the phase change. That will be related to the free energy, the enthalpy of phase transformation. Excuse me, this is free energy, it's enthalpy now. Excuse the errors in speaking, please. The enthalpy of phase transformation times the degree of undercooling, which is T transformation, the temperature at which you would have transformed if you cooled infinitely slowly, minus the temperature at which you're actually transforming over the equilibrium transformation temperature. So you can say that the volumetric energy for the that's driving the transformation is going to be the enthalpy of transformation times the degree of undercooling. More undercooling, more drive. And so you can see that as a function of the radius of the particle, looking at the red curve at T1, little bit of undercooling. You have to get a much bigger particle to get to the maximum, and you have a much higher energy barrier to overcome as corresponding to that delta G1 star. If you give a lot of undercooling or a lot of strain energy or other volumetric drive for the transformation, you lower the barrier and you shift over to a smaller radius for stability. So this should be ringing bells with anyone who's familiar with chemical kinetics. What we're effectively doing is using undercooling or strain energy as a driver, not just to drive the overall transformation, but also to lower its activation energy. Not only does it become more favorable, it goes faster. And that's important to us because our microstructure is limited by the rate of diffusion, so a process that is going to happen faster is less diffusion limited. So we can take the radius at which we suddenly hit the maximum, when we hit the maximum of these curves, and define it as the critical radius for nucleation. Any nucleating particle that is smaller than that will tend to dissolve. Anything that manages to get bigger will spontaneously continue to increase in size and grow at the expense of the other material. So that already sets the stage for excuse me, the scale of the microstructure that you get. So that is a very quick snapshot of nucleation and growth and how state variables and changes in state variables and drives relate through surface energy to the scale of the microstructure that we will get. And again, we've really only considered two: undercooling for a microstructure that is transforming on solidification and cooling, and then strain energy for something that's recrystallizing. Okay. In addition to the size of the nucleus, we can also look at the number that will form per unit time, and this is a purely kinetics argument that's somewhat independent of the previous argument. We can look at the nucleation rate, and this should be looking a little bit like our Fick's law diffusion coefficient, and thinking in terms of jump frequency. But this is the rate at which we will nucleate new particles of that second phase. Whether or not they'll grow, we don't know, but this is the rate at which we'll get new ones from the parent material. In addition to having the growth rate and the growth drive be dependent on undercooling, the nucleation rate itself is dependent on undercooling, which you can see with that T transformation minus T. So we actually now have a triple dependency on undercooling or strain energy drive for a transformation. So the lower the absolute temperature or the higher the strain energy is another driver, below equilibrium, the faster the new phase will nucleate. So we have triple dependence. So let's look a little bit more mechanistically on what it takes to transform one phase into another. And we're going to use our austenite to cementite and alpha ferrite from our iron carbide phase diagram to do that. So if you want to grab your favorite copy of your iron carbide phase diagram and have it in front of you, that'll be handy. You might want to get a wall chart of that for this portion of the class because it's very convenient to look up and walk your way around it. So if we imagine a eutectoid microstructure or proeutectoid up in the austenitic range, we're probably in the range of less than 1% carbon on an atomic scale. So fewer than 1 in 100 atoms in the lattice are going to be carbon. So carbon's pretty spaced out. When we dip down below the eutectoid transformation, you're going to have regions there that are cementite, the Fe3C intermetallic, in which case 1 in 4 are going to be carbon. So you had to take a lot of carbon from a long ways away and concentrate it all in one place just to get those layers of cementite. So that's an awful lot of diffusion that's going on in order to form that cementite phase, which is one of the reasons that it's easy to inhibit. So we can take a look in the context of just that phase transformation or others that are like it and look at how the rate of that transformation depends on temperature and elastic strain energy, remembering that temperature is going to hit in two ways. Higher temperature will give us the ability to rapidly diffuse that carbon, But the lower temperature we have, the higher the drive we have to want to form the cementite phase in the first place. So we will have a kinetics versus thermodynamic drive kind of a battle there, just the way we did with volumetric energy versus surface energy in forming new phases in the first place. We'll look at what it takes to slow the transformations down so that we never get the equilibrium microstructures, especially in the context of this particular transformation. And then we'll juxtapose which one do we want in terms of mechanical properties. We want the equilibrium structure, non-equilibrium metastable structure, or maybe something partway in between. Rates of phase transformations. As we kind of concluded, just looking at our 1% carbon moving into what's effectively a 25% carbon region to go from an austenite to a cementite, we know phase transformations involve moving a lot of atoms, and they move by diffusion. Diffusion's slow, and it gets a lot slower the lower temperature we go to. And unfortunately, but the thermodynamic drive for most of our commercially important phase transformations is undercooling. Definitely, so we lower the temperature in order to drive our transformation, and we saw that undercooling drove it hard in at least 3 respects: rate of nucleation, nucleus radius that was stable and would continue to grow, and then the energetic barrier to grow. But yet, if you can't move atoms to rearrange in phases, it's not going to grow regardless of the drive. Oops. So we have kind of 2 big trends that will define the scale of a microstructure, which we already know is important for mechanical properties through the Hall-Petch relationship for grain size and yield. If we have a high degree of undercooling, so our transformation temperature, which is presumed to be higher, minus our actual temperature, we are talking about cooling, so high undercooling is a high T trans minus T, we're going to have a higher nucleation rate and a slower growth rate. So the higher nucleation rate is coming from that volumetric drive being higher that we discussed at the first part of the lecture today. And then because the temperature is lower, the absolute temperature is lower, our diffusion rate is lower, so the growth rate is lower. And my goodness, we are seeing QD over in that right-hand expression. That is the activation energy for diffusion. Here it goes again. So if you think about what needs to happen to actually accomplish a phase transformation, something's got to diffuse somewhere. So we get to use our Fick's law expression again, or at least our expression for diffusion coefficient, which we could then use in Fick's law to actually calculate a rate. So as we increase the degree of undercooling, higher nucleation rate, slower growth rate, we're going to get a finer microstructure and typically superior mechanical properties. This is a very, very general trend regardless of the actual nature of the microstructure. You can superimpose this trend on perlite, on a single grain solid solution, on an equilibrium 2-phase structure. It's going to hold regardless. Okay, so let's apply it to a eutectoid composition in steel. We're going to take a eutectoid composition steel, denoted by the little vertical dotted line between the yellow star and the red star, and we're going to cool it down below the 727 degrees C eutectoid temperature. And we're going to look at what happens. Now we saw this lamellar growth front in the iron tin system in our phase diagrams discussion in reference to the formation of a eutectic and how we were able to get this massive amount of atomistic segregation to form this lamellar structure very easily in a eutectic because all of that segregation was happening in the liquid out in front of the growth front, and diffusion in liquids is pretty zippy. Well, now it's happening in a solid. This is a eutectoid transformation. So we've got a lot of thermodynamic drive. We're below the eutectoid temperature. In fact, we might be well below it. So we have a tremendous drive for the carbon to want to get out of that face-centered cubic gamma phase and form cementite, leaving carbon-depleted alpha between. But it's got to get there. So if you look over into the right-hand little schematic, you can see our growth front starting on an austenite grain boundary, of course. and it's growing out into an adjacent austenite grain. And you can see those little black dots are the carbon atoms moving as fast as their temperature will allow them to diffuse to the cementite growth fronts, those pink layers, that's the Fe3C, and attaching in a 4-to-1 ratio with iron and leaving a depleted iron region to deposit as almost pure body-centered cubic iron and make more alpha between. So a lot of carbon diffusion is having to happen. And so if we don't give it a lot of time, it's a lot easier for it to not have to go as far. So you can think of the sort of the vertical scale of the placement between those cementite and ferrite plates as being a function of how far the carbon had time to diffuse. And so if it doesn't have time to diffuse very far, those plates are going to be very, very finely spaced, and we will have what we call fine pearlite. In an extreme case where we don't give it much time to diffuse at all, it will actually form an alternate structure. It's still multi-phase, so we haven't gone to something metastable yet, but it's distinctly different from pearlite, and yet it's still composed of ferrite and cementite. It's called bainite. So we'll actually get a little bit of difference in arrangement if we really slow down, or excuse me, increase the rate at which carbon would have to diffuse, and slow it down as well by giving it a lower temperature. So we can look at the effective temperature on the percentage of pearlite that may have formed at any time. Say we're cooling an alloy down, and maybe we have a big billet that we're heat treating, and we've taken it out of the furnace and we're letting it cool in air. That's known as a normalization treatment. And someone says, well, gosh, when's it going to be transformed? Maybe you have someone waiting to do a follow-on process and want to know when it can be moved, for instance. There are quite a few diagrams, handbooks that you can use that have empirical data for given standard sizes based on heat transfer and transformation rates, where you can look this up. And this is an example of one type where you have time on the x-axis on a log scale and the remaining fraction, or excuse me, the increasing fraction of pearlite. This would be the remaining fraction of austenite. And so for a low temperature, the red line, at 1 second, you've got a tremendous amount of undercooling there. In about 1 second after you took this particular sample from austenite temperature to 600 degrees C, you would start rapidly increasing the fraction of pearlite, and the transformation would be completed in about 10 seconds. If you did this same transformation much closer to the eutectoid temperature and gave it much, much less undercooling, the transformation really wouldn't kick off until after 10 seconds, and it would take the better part of a couple of minutes to occur. It would still get there. So in this case, the effect of the undercooling drive is dominating over the effect of the slower diffusion, probably because at 600 degrees C, diffusion is generally still pretty fast. So the red curve at 600 degrees C, we would expect that to give us a much finer pearlite, and the green curve much coarser. Okay, speaking of empirical data, steelmaking especially has a tremendous amount of literature and study and handbook data. And one of the most valuable types is what's called an isothermal transformation diagram. And this is a collection of data that basically says for a given temperature and a given amount of time from cooling from some point in the austenitic range to that temperature, how much of each phase will you have? So it's basically like a virtual cooling, say a virtual walk through the phase diagram, except it's focusing on kinetics. So, and all of these diagrams are specific, of course, to pressure, 1 atmosphere. They're specific to a given composition. And also, although it doesn't say it on this slide, they're usually specific to a given prior temperature and time in the austenite regime. So that would be the austenization temperature and time. That's just a little aside. This type of transformation diagram is available for other commercial alloys, not just steels and ferrous alloys. These could be assembled for just about anything. They're very expensive and intensive to form and collect because effectively every single data point is a unique sample that's been heated up and transformed under controlled conditions in a controlled furnace and then quenched and sectioned and evaluated to see, usually with optical microscopy, to see what the fraction of phases are. And prior to the advent of image analysis, that was done laboriously by counting on a grid fraction of phases through a microscope. So these are very, very valuable, and many of them have been computerized. And so these become the foundation of heat treatment processes for many metal alloys and now some ceramics. So having said that, let's use one. So let's assume that we have a eutectoid composition. That's the 0.76 weight percent carbon eutectoid. And we are going to transform it. We're going to take it out of the austenizing furnace and we're going to put it in another furnace at 675 C, just 50 degrees C below eutectoid temperature, and let it transform. We'll assume that it's a fairly thin sample or a thin part, so it's isothermal, so it's all going to transform at the same time. We're going to assume it doesn't have any big temperature gradients across it. So we take it to 675 degrees C, and at 1 second you can look up to our gray line that we're going to follow from the left-hand side of the diagram to the right, there on the lower diagram. And at 1 second, nothing has happened. And at 5 seconds, nothing has happened. And in fact, nothing really happens until we get to about 20 seconds, where our big, thick gray arrow hits the green curve, which represents 0% perlite. And that's reflected with the dotted line up to the upper diagram with the percent transformed on the y-axis. So that's the point where it is going to finally start transforming. And from that point, the transformation goes fairly rapidly. At about 100 seconds, half the austenite that was originally present has transformed to perlite. And by what looks like maybe 500 seconds, it's all transformed. So that just gives you an idea of how we can track the rate of transformation. Okay, we can do this for various different temperatures and walk across the diagram. So in this case, we gave it a little bit more undercooling, so we would expect it to transform a little bit more quickly. So the diagonal portion of that black line that we just put in on the animation represents a very rapid cooling. That would be a quench, we call a quench and hold, where we started at a temperature above eutectoid, which is shown there in the blue portion of the diagram. We cooled very quickly, didn't give any time for anything to transform. And then we held at 625 degrees C, and we waited, and we allowed the microstructure to transform isothermally, hence isothermal transformation diagrams. So in this case, it didn't take nearly as long. We started forming perlite after, maybe a couple of seconds, and by 10 seconds we were done. We were all perlite. So same composition, same phase diagram. All we did was we gave it another 50 degrees of undercooling. And I could just about guarantee you that the perlite I formed from this one was finer than the one that we formed at the 675 hold. So this is our microstructure shot, and in fact, if you were constructing this from samples, these would be exactly the type of images that you would see. Which, by the way, notice you're going to do this optical microscopy on a hot stage because you're doing this at 625. So that's another reason that this is expensive to do. So that's how your microstructure would change with time at that isothermal hold. And this is what it would look like for real. Different gauges of perlite. This comes right out of the Callister textbook. Okay, what if we weren't right at eutectoid temperature? I mean, let's go for a high carbon steel and see what it's going to do. And we can get an idea of how much more complex the diagram is looking at our left-hand isothermal diagram. We've got a couple of extra curves now because we've got extra phases that form. So in this case, we have multiple boundaries starting with the blue one, and that's the boundary between austenite and cementite, and that's our primary cementite. Because remember, as we drop down in temperature, the first thing we're going to form is cementite in that gamma plus Fe3C two-phase region, and it isn't until we drop below eutectoid temperature that we would get the eutectoid cementite as part of our lamellar structure. So if we had cooled right down to eutectoid temperature and maybe just a bit below it, we would be eligible to form the eutectoid because we are below eutectoid temperature. Thermodynamically, it is possible. But looking at our left-hand side curve, we would start forming the primary cementite much earlier if we were just to hold at, say, 726 degrees C. Looks like they're both thermodynamically stable. Why don't we just form eutectoid and primary eutectoid at the same time? There's a lot more drive to form that primary eutectoid because we're 200 degrees from the looks of it below the equilibrium temperature which it wanted to form. So it has a much higher drive to form, and so even though we have now quenched down below the point where we could form the eutectoid, based on our composition, we have much bigger drive to form that primary cementite first, but eventually we would form the eutectoid as well, depending on which temperature we were holding at. And we would eventually get this microstructure. A very, very useful microstructure is one that we get if we wait long enough for the cementite or Fe3C particles to spherodize. So if we think back to the beginning of this chapter where we discussed the concept of surface energy being kind of the enemy to new nucleation, being the barrier energy that opposed the increase in growth, the increase in volume of our new nucleated phase. You can imagine that if we allowed our new phase to assume a low surface energy configuration, that would be energetically favorable. And one way that we can use that to our advantage is to allow cementite to precipitate from a different starting constituent and then literally cook it. Leave it in the furnace at a reasonably high temperature, close to eutectoid, maybe above 650 or so, and let the drive for reduction in surface area go from maybe a platy structure or an angular cementite precipitate particle to a sphere. Excuse me. If you have a fine network of these spherical cementite particles, you can still get excellent strengthening. This would be akin to what you'd get from a dispersion strengthening like we discussed in our strengthening mechanisms. But because the particles are round, they are not very prone to nucleic cracks. So this particular microstructure where we have allowed surface energy to reduce our cementite precipitates to its low energy state, our spherical low surface energy, low surface area state, we have a beautiful, fairly high strength, high yield, and very high toughness microstructure. So quite often we will go through a metastable phase to get there. We'll go through martensite, which is extremely highly strained phase where the carbon remains close to in solution in a body-centered tetragonal type of crystal structure. And then we will precipitate the spherodites out from that. We'll talk about martensite here in a minute or two. But this is an example of what you can achieve in terms of an excellent combination of properties just by performing an isothermal hold in a way that takes that surface energy and using it to your advantage to make things round. Okay, speaking of martensite, if you remember back to allotropic transformations and crystal structure of iron, your austenite, your higher temperature phase of iron, is face-centered cubic. and yet your room temperature crystal structure for iron is body-centered. And we touched on the differences in size of interstitial positions, especially those big octahedral holes that you have in the center of your face-centered cubic crystals, and how those are great for holding large amounts of small solutes like carbon. Well, that's one of the reasons why the solubility range that you see on the iron carbide phase diagram for austenite is so broad. That face-centered cubic crystal structure allows austenite to dissolve quite a bit of carbon. And the problem is when you drop down below any of the phase boundaries and start rearranging that iron into a body-centered cubic, it no longer has the large interstitial positions necessary to easily accommodate carbon. And so the iron atoms start to move around the carbon, and if the carbon can't diffuse away and start concentrating in a stable cementite phase, it gets trapped, and the carbon atoms continue to rearrange into a body-centered cubic and become strained and out of their equilibrium positions. Well, we know from our bond energy discussions way at the beginning of this course that anytime you have atoms that are not in their equilibrium positions, we've induced strain energy. So now the carbon is acting as a potent solid solution strengthener, pushing the iron atoms off of their equilibrium positions that they would like to assume in a body-centered cubic. This can happen to an extreme extent if we rapidly cool iron. What we'll do is effectively trap a tremendous amount of that carbon in its non-equilibrium position and force the iron atoms to rearrange around it in what's effectively a completely different crystal structure than it wanted to achieve. It will kind of end up stuck halfway between a face-centered cubic and a body-centered cubic, an arrangement called a body-centered tetragonal, which is basically a body-centered cubic that's extended upwards to the point where it has a C-axis instead of just an A-axis. It's not a cubic anymore. It's got a longer axis in the Z direction, and with too much carbon in interstitial positions, octahedral and to a lesser extent tetrahedral holes. This body-centered tetragonal structure, again, it is not an equilibrium structure. It will only form when diffusion is too slow to allow the carbon to get out of the way and allow the iron to rearrange into a stable body-centered cubic structure. And so we call this a metastable phase. It has a tremendous amount of strain energy. Every single iron atom in that crystal lattice is in a non-equilibrium position. The entire lattice is strained in 3 dimensions. And because of that, it has a hardness and a strength that exceeds just about any other metal that you can achieve. It is practically on par with most ceramics. Regrettably, its fracture toughness is right on par with most ceramics. Furthermore, being metastable, it's prone to spontaneously transform under the influence of heat, pressure, sometimes even time. Or additional cooling if necessary. You can have face-centered cubic iron that doesn't transform to body-centered tetragonal or body-centered cubic. That's known as retained austenite, and it is also unstable or metastable at room temperature. So retained austenite and martensite are the 2 metastable or non-equilibrium structures that we can get when we rapidly cool iron. The more carbon you start with, the more carbon there is to get in the way of transformation, the more carbon that must diffuse away for iron to go from its FCC to its BCC equilibrium position. So the more carbon that you have in your starting steel, the easier it is to form this metastable body-centered tetragonal martensite, and the harder and stronger that martensite will be when you form it. Also the more brittle. So again, we can use empirical data to determine how fast we have to cool if we want to get martensite, or how slowly we have to cool if we don't want to get it. And it is very useful for adding mechanical properties. We just can't use it in its as-formed condition because of its low fracture toughness. So we can look at an isothermal transformation diagram, and this one obviously includes only very, very fast cooling rates. It's specific to a particular alloy composition and prior austenite time temperature treatment. In this case, we're looking at our diagram on the lower left, and we're starting at the top of our gray line at 800 degrees C, and we are going to cool very rapidly. So anytime we drop along a line on an isothermal transformation diagram, that we're not following a horizontal, we're assuming that we're cooling so fast that we're giving nothing time to transform. This would be equivalent to what we would call a quench. So we are going to quench from around 800 degrees C to somewhere well below 200. So we are not going to give time to form perlite. We're not going to give time to form bainite, which is the rapid transformation analog to perlite, but still equilibrium. We're not going to form anything except martensite. And something to remember about martensite is because it forms spontaneously on rapid cooling, it's actually what's known as a diffusionless shear transformation, more like twinning than the diffusional transformations that we've learned about from phase diagrams so far. It's diffusionless because it happens literally because the carbon didn't have time to diffuse. So no diffusion is involved in forming martensite from austenite. What happens is atoms will rearrange in a pseudo-twinning process, in a shear process. So it's not time dependent, but it is temperature dependent. So on isothermal transformation diagrams, the proportion of martensite that you have versus your starting austenite will be shown in horizontal lines. So the cooler you get, the more austenite has transformed to martensite. Sometimes those lines go below room temperature. And that's where we get what I'd refer to as retained austenite, where you can have face-centered cubic iron austenite at room temperature. It has not formed perlite, it has not formed ferrite, and it hasn't formed martensite. It's totally stuck. That's a very unstable phase. And in fact, it can be induced to form martensite simply by giving it a little bit of impact. In cases where we want to form 100% martensite from those, we'll actually quench to below room temperature. And if you've ever heard of cryogenic quenching, that's why you do it. So just looking at the microstructure, if we did an optical micrograph of our sample that we've quenched down our gray line, we would see the structure over on the upper right, where the dark areas are needles of martensite and the white areas between them are retained austenite. Okay, so a little flow chart of martensite formation. If we slow cool, we don't get it. We'll just get our alpha, ferrite, and cementite either in a perlite structure or hypoeutectoid, and perlite, or the very fine analog to perlite, bainite, which is still ferrite and cementite. If we quench really fast and we don't give that carbon time to diffuse at all, we will go through our diffusionless shear transformation, and we will get our body-centered tetragonal metastable structure, which we call martensite, so hence the M. So it is single phase. Again, body-centered tetragonal crystal structure, highly strained, very brittle, very strong. It's really best to think of it more like a ceramic. In some of the early days of making razor blades, they would sample alloys of untempered martensite would be dropped in the lab and crack just from the impact of hitting the ground in the lab, and that gave untempered martensite the name tinkalloy from the sound that the samples would make as they shattered, just like a ceramic. So you can think of martensite as being tinkalloy, very low fracture toughness, not something you would want to use in its as-quenched state. If, however, we move a little bit of that carbon, not much, but a little bit, into an equilibrium structure. We form a little bit of cementite, and we relax the strain energy out of that structure, that metastable structure. We get what we call tempered martensite. And without losing much in the way of yield strength or ultimate tensile strength, we regain a tremendous amount of fracture toughness. And that is a treatment known as quenching and tempering, and forming a tempered martensite structure. If we give that tempered martensitic structure longer time at temperature, eventually the carbides we form, the cementite we form, will ball up and we'll end up with a spheroidized structure, which again is not as strong as tempered martensite that hasn't been held in its tempering temperature quite as long, but is very, very tough. So you can think of spheroidized steel as being a long duration extension of tempered martensite, because that's what it starts with. Needless to say, the need to quench, which requires a tremendous amount of control, dimensional control, heat treatment, very expensive facilities, and the long times at temperature, both for austenizing and then the after quench tempering, means these are expensive processes. So a quenched and tempered steel will almost always be far more expensive than an equilibrium microstructure. And of course, then we have to add the cost of machining it. And in fact, since they are so hard, quite often they are at least rough machined to size before quench and tempering treatment. So we can go through an example and just very quickly, we'll just walk through this with the animations. We're going to look at an isothermal treatment at 800 degrees C and see what we get. So we took the alloy out of our austenizing furnace at 800, above 800 C. We dropped it to just below eutectoid temperature, and we can look at our diagram and predict what we got first. We started on our aqua line. We started precipitating out our alpha ferrite phase at sometime around 0.2 seconds. So before even 1 second we were starting to precipitate. Sometime just shy of 10 seconds. We were in a regime where we had both perlite and ferrite, so we were starting to grow some perlite at that point. We had completed all of our perlite growth by sometime around what looks like 100 seconds, and any further time at temperature would do nothing but coarsen the perlite. Any austenite that had not transformed would transform to martensite when we quenched. But from the look of it, because we crossed the red line, which corresponds to 100% transformation, there was no austenite remaining to transform to martensite. So we had an all ferrite perlite structure. The dotted line in the middle of the diagram with a P on the upper end and on the upper side and the B just below it, that is the demarcation for perlite versus bainite. And again, those are both decomposition structures where carbon will diffuse from austenite to form alpha ferrite and cementite, but bainite is a finer structure. The order of diffusion, the order of phase formation is a little bit different, and it will be stronger due to the finer scale of the microstructure. So it is still a diffusion based microconstituent, not diffusionless shear like martensite, but it tends to be a good deal stronger, a little bit less tough, and so it's quite often called out as its own portion of these diagrams, because there's circumstances under which you would want to achieve it when you need a little bit more strength. And it looks different in an optical micrograph, so you can identify it. We can identify at certain times through the transformation what weight fraction we have, and we basically just use the position between the onset and completion of different regions in much the same way we used a tie line on a phase diagram. So what if we wanted to get something really hard? Somebody paid us a lot of money and we were going to do a full quench and temper treatment, and the first thing we needed to do was make sure we made nothing but martensite. We don't want any alpha ferrite, we don't want any perlite, we don't want any bainite. So this is the type of cooling profile that would give us 100% martensite. We had to cool very fast. If you look at the time that we had available before we start to hit the onset of the alpha ferrite formation or the bainite formation, they're just below 600 degrees. We had to get that entire part below that temperature by in less than 1 second. So I hope it was a very thin part and a very effective quench bath. This is this bend the nose, it's called, in the isothermal phase transformation diagram, where the onset of formation of decomposition microstructures is called the nose, and it basically sets the rate at which a part has to be quenched in order to get 100% martensite. One of the roles of adding alloying additions to steel is to move that over to the right so that a slower quench can be used and still get 100% martensite. Because if you remember from what we know about coefficient of thermal expansion, if we change the temperature of something really, really fast, we strain it. Those atoms will move to a new position, and that can induce stresses. Additionally, going through the martensitic phase transformation, there's a tremendous change in volume that produces a lot of stress in the material, and so we're very subject to what's called quench cracking due to both coefficient of thermal expansion and the volumetric expansion of the martensitic phase transformation. So it's always better to be able to form what we want with slower cooling. Besides the fact that in a thick part, it just may not even be possible to cool the center that quickly. So shifting the onset rate of those decomposition phase transformations over to the right is called increasing a steel's hardenability. And that just means it's easier to form 100% martensite. If we didn't quench to a low enough temperature, for instance, and we held our temperature somewhere around 300 degrees C, we would only get 50% martensite. The rest would be face-centered cubic austenite forever until we dropped below the martensite finish temperature, which looks to be around 225 or 50 degrees. So this was a whirlwind tour of quenching and metastable transformation here. You'll have to practice a few of these to get used to it, but basically it works a bit like the phase diagram. You're just marching across the transformation at a single temperature. Okay, talked about moving that nose over. This is an example of a highly hardenable steel. It's probably 4130 or 4340. And you can see how all of those onset regions for forming alpha ferrite and pearlite and bainite have now been shifted quite a bit over to the right. And in fact, the first one to form now takes 10 seconds. Whereas if we look at the slide before, we were starting to get alpha ferrite and bainite forming at less than 1 second. So obviously, if we can quench from austenite temperatures down below 500 or 450 in 10 seconds, we can form 100% martensite. So especially if we have a thin part, that's very doable. And the type of alloying additions that will do this are things like chromium. Molybdenum is very powerful. In particular, these are all what are called hardening alloys. Alloying additions, and they don't themselves make the alloy hard, not in solid solution, and in fact they are not added in very large quantities. These are all added at far below the threshold for solid solution strengthening. What they do is they make it easier, they make it harder for the carbon to rearrange itself and decompose into cementite, and in so doing they make it easier to make martensite with a slower cooling rate. Okay, carbon content, because not all martensite is the same, and not all of our decomposition steel products are the same. So how does carbon content, what is its effect on the continuous phase? So obviously, if we're contrasting hypo versus hypereutectic, it completely alters the continuous phase. If we're in a hypoeutectoid steel, excuse me, I didn't mean to say eutectic, eutectoid, we're steels, it's all eutectoid. If we have less carbon than the eutectoid composition in steel, our continuous phase will be ferrite. If we have more carbon than the eutectoid composition and we're a steel, our continuous phase will be cementite. So the first and greatest effect carbon content will have on steels is what is our continuous phase? Hypoeutectoid steels with a continuous phase of ferrite are going to be softer, tougher, less strong. Flip side, hypereutectoid, these will start to overlap with your heat-treated bainitic steels and your martensitic steels in terms of strength, and will tend to be low on fracture toughness. And the graphs below just give you some examples of how that can go. Again, look, the blue side of the graph is your hypoeutectoid side, where you have continuous ferrite. As we increase the carbon content, we start to ramp up our properties on a more or less continuous basis. And of course, our impact energy, which is a qualitative assessment of fracture toughness, decreases rapidly as we go across and remains very, very low as we cross the boundary and have that continuous cementite phase. Now again, we can alter this somewhat by making it thinner, refining our microstructure, but those are the general trends that we get. Higher carbon is higher strength, higher yield strength, lower elongation, lower fracture toughness. Now, again, said we can alter that with heat treatment. What if we take that continuous cementite and start making it discontinuous, balling it up with a spheroidizing treatment? This is where we can see that best of both worlds. Excuse me, over on the left-hand side, we're now comparing carbon content across our steel range, going hypo to hypereutectic, but this time we're rearranging the microstructure and comparing fine pearlite, coarse pearlite, and then our balled up cementite, spheroidite, from our spheroidizing treatment. This time we're using Brinell hardness as just an indicator of all of our strength mechanical properties. This is sort of a large-scale hardness test, which can be thought of as an average of yield strength, tensile strength, and so gives us an indication on that side. And then ductility and reduction in area being our indicator of also fracture toughness as well as ductility for forming. And you can see that as we make the pearlite finer, we get a big boost in hardness. So this would correspond to an increase in yield and tensile strength. We do get a bit of a hit in ductility, but there is a smaller reduction in our ductility properties, a smaller reduction in our fracture toughness compared to our increase in strength. So it's a net win. We give up less fracture toughness than we gain in strength when we refine the microstructure and go from coarse to fine pearlite. The extreme of that is spheroidite. We definitely give up strength with spheroidite, even versus coarse pearlite, but we gain tremendously in fracture toughness as indicated by our ductility. Remembering on our uniaxial tensile test curves, ductility reduction in area, if we correspond all the way to strain at failure, that is our fracture toughness. So the two are correlated. So this is one of the reasons why that expensive type of heat treatment necessary to achieve the spheroidized microstructure might be worth it if you needed this combination of properties. Okay. Even in the world of martensite, not all martensites are the same. So if you look at our purple curve, if we march across our steel making range of compositions, going from 0% carbon all the way over into the hypereutectoid range, say we quenched and we formed 100% martensite in all cases, which at our lowest carbon end is nearly impossible to do, but say we were able to do so, even at 100% martensite, the more carbon we have, the harder, stronger we're going to be. And in the case of fine pearlite, If we went the other direction, formed no martensite, we would see the same trend. Obviously, we're going to get a much stronger microstructure with martensite irrespective of the amount of carbon. So going all the way over to a very high carbon steel but not forming martensite isn't going to touch what we can get with martensite irrespective of the amount of carbon. So general rules of thumb: if strength is the big determiner, nothing will be as good as martensite. If you need anything else, you have to start considering other microstructures. And this gives you a little bit of a semi-quantitative estimate of what happens when you temper martensite. Again, we never want to use it in the untempered state unless we have an application where we would be okay with a ceramic, which is pretty much none for monolithic materials. So you can see how as we increase our tempering temperature for a given time, we start marching from the left to the right on our left-hand side diagram. So we're going to drop our yield and tensile strength as we release the strain energy in that metastable body center tetragonal lattice, and we're going to increase in our reduction in area, which is an indicator of fracture toughness. So somewhere in the middle part of the diagram, before the lines cross, we probably want to stop. Again, balancing those properties the same way we did with recrystallization and strain recovery for cold work. At some point we're going to choose our tempering temperature and time and decide how much of the carbon we want to take out of that body center tetragonal strained lattice, and how much fracture toughness we need to recover and how much strength we're willing to lose. It's all a balance. So this gives just another quick review of what we can form from austenite. Just a quick review of our phase transformations. It's probably best to have your iron carbon phase diagram in front of you when you look at this. So if we're starting with face-centered cubic austenite with some carbon dissolved in it, we can slowly cool and we'll get pearlite, and we'll get either alpha ferrite or cementite as a proeutectoid phase, and the pearlite will be fine or coarse depending on exactly how slowly we cooled. If we cool a little bit faster, we'll get finer pearlite, and then we'll get bainite, which is our very rapidly cooled but still decomposition product. If we cool very, very rapidly, we will not allow the carbon to diffuse at all. We won't get any decomposition products and will form martensite, which we will, of course, reheat and temper before we put it into any structural use. And if we continue to heat it, we will eventually get spherodite, and we will lose strength, but we will achieve tremendous amount of ductility. So this just gives you the general trends, how every one of these different potential microstructures ranks up relative to the other. And of course, they all come with a different associated cost, fortunately. And this is from I believe the 5th edition of the Callister text, which is just a quick snapshot of all of these different things. If you need to pick a microstructure, this gives you a quick and dirty guide. Okay, last but not least, precipitation hardening. And this is used almost exclusively in non-ferrous alloys. The two noteworthy ones are aluminum, especially the 2000 series aluminum copper, the 6000 series aluminum magnesium silicon, and the 7000 series aluminum zinc, with a few other alloying additions, and beryllium copper. Those are the two big structural systems where this is the mainline method of strengthening. And so for this we are going to we're still going to use a metastable condition, but we're going to go to quite the simpler side of the phase diagram. So we're going to look at an alloy with a composition of A up on our aluminum copper phase diagram. So it's way over on the aluminum rich side, very little copper. And right now we're going to start it in its solid solution phase. It's all alpha there, somewhere around 525 degrees or so, and we're going to cool it and see what happens. So first we got it to that temperature, made sure it was a nice uniform composition. It's called a solution treatment. Then we're going to quench it all the way down to room temperature. we aren't going to let anything happen. So this is akin to forming martensite in a way. We're not going to form a metastable phase, but we are sure as heck going to prevent that CuAl2 intermetallic from forming. So this is very akin to quenching austenite and not allowing cementite to form, but this time we've just locked all of the copper into solid solution in the alpha. We haven't formed it is still a metastable solid solution, but it doesn't have anywhere near the strain energy that we would get from martensite. So we didn't have a diffusionless shear transformation, but we did deviate from equilibrium. So what we have now is a metastable solid solution, and it has some reasonable strength, but not nearly as much as it would have if we reheat back up to a temperature C and start letting the copper atoms reorganize just a little bit in preparation for forming that CuAl2 intermetallic, but don't actually let it get to the point where it has a phase boundary. We're going to let its thermodynamic drive to associate with itself actually volumetrically form some CuAl2, but we're going to make sure that the edges of those precipitates stay coherent with the parent lattice. That means they're going to be strained off of the positions they'd really like to assume, and we're going to introduce strain energy into the lattice the same way a solid solution does, the same way the martensitic transformation does, but not quite so much, but enough to give a lot of strength. This is called forming coherent precipitates, and it is the heart of the precipitation hardening process and what gives it its strength. Because the strain associated with all of those CuAl2 atoms on the edges, on their surface boundaries, not being exactly where they want, impedes dislocation movement, just like jamming a bunch of solid solution atoms in or straining the entire iron lattice in martensite. It all works the same way. Strain energy impeding dislocation movement. So this is one of the last slides of the day, so hang with me here. We're almost there. We're going to step through just real quick mechanistically what's going on to achieve that strain energy, because it does sound a little esoteric until you see the cross section. So when we drop our alloy composition A down to room temperature, we have a lattice that we see over on the left hand side. We got some copper atoms there. We got more than we really should have at room temperature. That's a super saturated solid solution. When we do the reheat at temperature C, some of those start to rearrange to form that nice intermetallic that you see in that shaded blue area. But look at how there's no real grain boundary. We've still got a correspondence of each one of those atoms back to the parent lattice. They're lined up exactly where they would be if they were still in the parent aluminum lattice. As such, notice how everything is bending in. You've got a lot of atoms with diagonal lines connecting them, and that's representing those atoms not being in their equilibrium positions and being strained. Those strain fields extend all the way out into the parent aluminum lattice and can impede dislocation movement all the way through the lattice, and that's where you get your strength. So if you look to our upper graph, we have strength or hardness as a log of aging time. So that aging time is the time at temperature C where we're allowing a few of those copper atoms to rearrange and form these coherent precipitates. We're going to stop them before they form a grain boundary. So you can see how we march up the strength curve as we go from a solid solution, oversaturated, still pretty strong, which you can see on the left-hand side of that red curve. We get to about as much as we can get from that, and then we start marching up the steeper part of the curve to a peak where you see the gamma double prime, and that gamma double prime is a industry standard term that indicates a coherent precipitate. If we leave it in the furnace, eventually we'll give it enough activation energy to form its own true grain boundary. And you can see we no longer have any diagonal lines. Nothing is pulled off of its equilibrium position. And we just have a second phase particle, which is still reasonably strong, but in most cases not nearly as strong as our coherent precipitates. And so that's called overaging, or formation of incoherent, meaning the lattices are no longer coherent with one another and we have a true grain boundary. There is still benefit to that type of structure. For instance, it tends to be far less prone to stress corrosion cracking. So again, we pick our microstructure to give us the balance of properties we need, but in almost every case, the coherent precipitate structure is our strongest. So we want to catch it at that point. So we can do it several ways. We can age at a relatively high temperature for a short time, or we can age at a lower temperature for a bit longer time. And depending on the alloy, one will give a stronger or weaker final structure. A lot of that depends on the time that you have available and your processing capabilities. Generally, you can get equivalent strength and elongation multiple ways. And again, the alloy will also be a determining factor there. So that is it. Apologies for the very long lecture, the whirlwind trip through important microstructural transformations. But hopefully you can see that what we've done effectively is balance a thermodynamic drive with a kinetic ability to move atoms necessary to form those new phases. And we've simply put those two competing roles in opposition and looked at the effect that that opposition can have on forming different microstructures with different properties and processing costs and implications versus what we can afford and what we need. So the remaining lectures and the remaining topics in this class will mainly center around real-life processing methods that can be used to achieve these, specific applications and consequences of using these different microstructures in terms of cost, sustainability, environment, and durability, corrosion in the service environment if that topic hasn't already been addressed. All of this has tremendous consequences in that direction. So we will see you next time for one of those topics.